Dear students, today we can discuss about the Hooke's Law and its applications. So in 1960, there was an English scientist, Robert Hooke. He conducted a number of experiments about the elasticity of solids under relatively small deforming forces. And he applied the different values of stress to a given material, and he measured the corresponding strains, and he found a relation between the applied stress and the strain, and he deduced a law by connecting the relation between these two quantities. And that law is known as Hooke's Law. And it states that the stress is proportional to the strain within the elastic limit. That is, stress is proportional to the strain, or stress by strain equal to a constant. And this constant of proportionality depends on the material being deformed and on the nature of the deformation. And this constant is called the modulus of elasticity or elastic modulus. Since we know the stress has a unit Newton per meter square, but the strain has no unit. So the unit of elastic modulus is same as that of the stress, that is Newton per meter square or Pascal. So when we consider the Hooke's Law, in the case of a wire, and if we applied a load to it in such a way that there is an extension, that is, there is a change in length happen to that material. So in that case, the stress is called longitudinal stress, and if is the force applied to the body, applied to the material, and A is the area of cross section, then the longitudinal stress is defined as the ratio of the force per unit area, that is equal to F by A. Since here there is a change in length, that is the deformation happened to that material, the strain in this case we call the longitudinal strain. Suppose L is the original length and delta L is the change in length, then the longitudinal strain is defined as the ratio of the change in length delta L to the original length L. So the longitudinal strain is equal to delta L by L. And this strain can be tensile, that is, if there is a change in, if there is an increase in length, or it can be compressive if there is a decrease in length. Okay. Now let us apply the Hooke's Law in this case. So since there is a change in length, the corresponding modulus of elasticity called Young's modulus. So here the Young's modulus is the longitudinal stress divided by the longitudinal strain. So the Young's modulus can be defined as the ratio of longitudinal stress to the longitudinal strain under a relatively small deforming force. Now let us have an expression for the Young's modulus. Usually we are using the letter Y for the Young's modulus. So y is equal to the longitudinal stress is F by A divided by delta L by N. That is the longitudinal strain. So when we arrange this, we have Y is equal to F into L divided by A delta L. Okay. Suppose we are for the elongation of the material. Suppose we are hanging a load to the one end of the material. Then the F should be M into G. M into G. And if the material is in the form of a wire, then the area cross section would be pi r square. That corresponding changes happen wherever the necessary. Now, in the figure you can see some of the materials are, the values of the Young's modulus of some of the materials are arranged in an order in this table. So you can see the steel has a Young's modulus 20 into 10 raised to 10 Newton per meter square, and copper has the value 11, brass has 9.1, glass is 5.5, the rubber has the value 0.05. So there are some questions that we can answer. Here, arrange the materials in the increasing order of their deformed length under unit external force. Consider that the materials given are having the same dimension before deformation. Okay, that means all the materials have the same dimension, and they are undergoing the same external force. Then what is the increasing order of the deformation? Okay, so here the steel has the higher Young's modulus. So when we apply the force, it would have the less value of the deformation. As we move from the top to the lower bottom, we can have the corresponding Young's modulus has a decreasing values. That means when there is a decrease in value of Young's modulus, that corresponds to, or that means that there is a increase in their deformation. There is an increase in their length under the same external force. So the order of the increasing order of the deforming length, that would be the order the same as that in the table. Okay. Then question number 2. Under a given external applied force, the glass and the rubber shows a 1 meter extension in length. Which one would be the thicker? Since the rubber has the lower Young's modulus compared to the glass, then for getting the same 1 meter extension, then the rubber would have been the thicker compared to the glass. And the question number 3. Come into the following sentence. A copper cable is cut into half of its original length. The maximum load it can support is the same as the previous load. Okay. The maximum load that it can support is same as the previous load. Here, the statement is true because since there is no change in the area cross section, the maximum load, that is the stress that it can support, is the F by A. Here here the length of the copper cable is cut into half of the length. That doesn't affect the load supporting capability of the cable. It depends on the force and the area of cross section. Which of the material given in the table is best to make the springs? Obviously, the steel is the best material because it has the higher value of the Young's modulus, and correspondingly it has the less deformation in the length. So it is the most suitable for making the springs. Now let us consider the change in dimension that happen in the case of a shape. So let us see. Suppose we are taking a thick book like a dictionary, and you can place it in the table, and you can apply a force, a tangential force parallel to the top surface. So what will happen? So you can see the book is a rectangular shape. So when we apply the tangential force on the top of the surface, the shape of the book gets changed. Now the shape of the book will become like a parallelogram. Okay, here there is no change in the volume of the book. Okay, so in that case we say that the body, the object gets sheared. The object gets sheared, and the force we applied, the stress we applied for making the body get sheared is called the shear stress. Okay. So that is when an object is subjected to a deforming force parallel to one of its faces, while the opposite face is held fixed by another force, the shape of the body is changed, and the stress in this is called the shear stress. And the process of deforming the shape of the object without changing its volume by applying a parallel deforming force to one of the faces of the object, and this process is called the shearing. Okay, here we should understand that here there is no change in the volume, only the shape gets deformed, that is the body gets sheared. Okay, now let us apply the Hooke's law in this case. For that, let us consider a rectangular block whose the lower surface is fixed, and we are and the area cross section is A, that is the area of the top surface is A, and we are applying a force, that is a tangential force, parallel to the top surface. As you can see in the figure, it is from left to right. So what happened? So the top surface gets sheared. Okay. That is here on the left, the top surface has a displacement delta x from in the left to right, and the corresponding the rectangular shape will become a parallelogram shape. So let us find the corresponding stress and the corresponding strain and the corresponding modulus of elasticity. Okay. Now here the stress is called the shear stress, and the shear stress is defined as the ratio of the tangential force applied to the area of the face being sheared. So the shear stress is equal to the tangential force per area, that is F by A. Okay, and here the shape gets changed, and the corresponding strain is called the shear strain. Okay, here the shear strain is defined as the ratio of the horizontal distance. Here the upper face gets sheared through a distance delta x, and the ratio of the horizontal distance delta x that the sheared face moves to the height of the object. So delta x, that is the change in the distance through which the shearing face gets moved, and it is to the ratio of the height h. Okay, so delta x shear strain is equal to delta x by h. Here we have an approximation, that is if the deformation is very small, the shear strain can be recognized as the angular deformation. So that is, if delta x is very small, so this delta x distance can be considered as a part of a circle, that is, it is an arc of a circle. And let us apply the relation between arc length, the radius, here the radius will become the height, and the angle. Okay, so the theta is equal to arc length by radius, that is delta x by h. Okay, so we can replace the delta x by h by this angular deformation theta. Okay, so the shear strain is equal to this angle theta, and this angle is called the shear angle. Okay, so in this case we are expressing the shear strain in terms of angular deformation theta. Okay. Now we apply the Hooke's law. So the Hooke's law, it is a ratio of the stress by strain. Here it is the ratio of the shear stress to the shear strain, and this modulus is called the rigidity modulus or the shear modulus. Okay, and we are representing the rigidity modulus by the letter eta. So eta is equal to, what is the shear stress? Shear stress we have already defined as the force by area, that is F by A, and the shearing strain is the theta. So eta is equal to F by A divided by theta, or eta is equal to F divided by A theta. So now this is the expression for the rigidity modulus. So what is the unit of the rigidity modulus? So as we have discussed earlier, the modulus of elasticity has the unit of the stress, that is a Newton per meter square. Whether it is Young's modulus, whether it is rigidity modulus, all this, and next we are going to see the bulk modulus. Okay, all the modulus of elasticity has the same unit, that is Newton per meter square. So let us consider, suppose you have a balloon. Suppose you have a balloon. It is already it has some size, some volume, and we press the balloon from the all sides with your hand. What will happen? If we press the balloon from the wall sides, from the wall sides of the balloon with your hands, so we can see the balloon gets compressed. Okay, and this happens only when we apply the force perpendicular to the surface over the entire surface. Okay, so here the force of uniform magnitude is applied perpendicularly over the entire surface of the balloon. Okay, so then the result is there is a deformation, that is there is a change in volume. Okay, and here this type of change in volume happens only when, as we had discussed earlier, only when the forces acting perpendicular to the surface. Okay, so when we consider there is a perpendicular force acting per unit area, that is the pressure. That is the pressure. Okay, so in this case, the volume stress, here there is a change in volume. So the corresponding stress is called the volume stress. So the volume stress is defined as the ratio of the magnitude of the total force exerted on the surface to the area of the surface. Suppose F is the force and A is the area. Now the volume stress is equal to F by A. Okay, as we said earlier, in this case, here the force is perpendicular to the area. So the force per perpendicular force per unit area is the pressure. Okay, so in this particular situation, the stress is the pressure. The stress is the pressure. Okay, so under the pressure, the object experiences a volume change delta V. Okay, suppose V is the original volume, then under this pressure, the object experiences a volume change delta V. Then the volume strain, here it is called since there is a change in volume, thus corresponding strain is called volume strain, or also called as a bulk strain. So it is a ratio of the change in volume to the original volume. So the volume strain is equal to delta V by V. Okay. Now when we apply the Hooke's law, here the ratio of the volume stress to the volume strain, and the corresponding modulus is called bulk modulus. It is called the bulk modulus and denoted by the letter B. So B, the bulk modulus equal to negative of P divided by delta V by V. So when we arrange bulk modulus B equal to the negative delta PV, the negative PV divided by delta V. Here there is a negative sign is inserted. For the purpose is that the B is always getting a positive number. Why? Because when we apply the pressure, there is a decrease in volume. So delta V should be a negative value. So when we put the negative value here, negative value for the delta V here, then there is already a negative value, negative sign is there. So we will have a positive value for the bulk modulus. For that purpose, we are inserting a negative in this expression. Okay. Now, when we take the reciprocal of the bulk modulus, it gives an idea about how much the volume of the material can be changed. So, and this value is called compressibility. The reciprocal of the bulk modulus is called compressibility and is denoted by the letter K. So, K is equal to 1 by B. So, that is equal to negative delta V by PV. Delta V divided by PV. Okay. So, that is an idea. It gives an idea about how much a material can be compressed. Okay. So, that is relevant in the case of the liquid and gases, and it is not significant in the case of the solids because it has already the particles are already tightly packed in the case of the solids. Okay. So higher the value of the bulk modulus, so it has a less compressibility. But lower the value of the bulk modulus, it has the high chance of the compressibility. Okay. So the material with a small bulk modulus have the larger compressibility are easier to compress. Okay. Now what is the unit of compressibility? So that is the reciprocal of the pressure. So it is equal to the per Pascal. Is equal to the unit of compressibility is per Pascal.